So when you're working out a mean value theorem problem, you usually start, if you're trying to find the C or see that the C exists or whatever, it starts by doing the right side of that, right? It starts by doing the slope between the endpoints. That's what you can usually find. Then you do the derivative and set it equal to that, and then you can find where that happens. Now, you didn't have to in this one. They didn't ask for it, right? They just said, show why there has to be a C such that it has a slope of 2. Well, you had to show that the slope between the endpoints is 2. That's what you had to do. So some of you were talking about finding slope or setting it equal to whatever, but you really need to do the slope between the endpoints to show that that's 2. That's why there has to be one that's slope of 2. Okay, there could be one, there's places in between there that have other slopes, right? But the mean value theorem just says there has to be one that has the slope between the endpoints. So you had to find the slope. Okay, all right, what else? 33, was that the one with the speed and whether he was speeding or not, whatever. Okay. And it was yes, he was, or something, wasn't it? I can't, it seemed to be on that one, the back of the book was wrong or something. I don't know if anybody looked it up in the back. Is it wrong? It seems to me over the years, if you look it up in the back, it's wrong. He went 100 miles in 1.25 hours, and so that means he was going at least 80 miles an hour. So that he was speeding, right? And then the fine would be like $125, because $5 for every mile an hour over, so $5 times 15, and then add that on to 50. So yeah, it seems like the back of the book had a wrong answer. Okay. Anything else? Any of the ones before that? Okay, what about, did we have to do 15 through 18? We didn't do those. Okay, let's look at those real quick. Okay, on 15 through 18, it talks about f of x equals square root of x. Or not square root of x, absolute value of x. So let's because these are the ones that are kind of like, the other ones we did with the other theorems. So let's talk about this section here. So if you look in your book there, where like does the conclusion. Some of the questions I had you do here were like if then, like converse, like if you flip it around, So for example, the converse is sometimes true but not always. So like if a function's differentiable. So one of the things I might ask you is some true false kind of things like this, right? So on tomorrow's quiz, I might ask you some of these kind of things. Like, for example, if a function is differentiable, then it's continuous, true or false? That is true. We said differentiability implies continuity, right? If a function is differentiable, then it's continuous, true. If a function is continuous, then it's differentiable. False, right? So all these different kind of theories and different things really lend themselves to those kind of questions, so that you can expect there to be some true, false, kinds of things like that, okay? Where, just there's not a lot to study for that. You just have to think your way through it. Okay, now, does so we know that the absolute value function is not differentiable, right? At least at 0 anyway. But it says, what if you look from -1 to 2? Okay? Does f satisfy all the hypotheses of the mean value theorem from -1 to 2? No.
Isn't that like this system is
Right? Mean value theorem is the one where it's got both things. It's got to be continuous on the closed interval and differentiable in between. So, does the absolute value satisfy the hypothesis? No, it's not differentiable. Does the function satisfy the conclusion? And the answer again is no. What is the conclusion? The conclusion is that there's got to be some place where the slope would be the same as the slope between the endpoints. So here's the slope between the two endpoints, which we can easily find. But we could just draw a picture. We could just say false, because it does say explain. So you could just show a picture, and you could say that there is no place between -1 and 2 that has that slope. Or you could actually calculate it. This would be y value 1, this would be y value 2. So this would be 2 minus 1 over 2 minus -1, and that would be 1/3. So this would have a slope of 1/3, right? Rise over run. There is no place, because what's the slope here? -1, slope here, 1. So on the absolute value graph, all the slopes are -1 and 1. And so there is no place that has a slope of 1/3. So this does not satisfy the conclusion, which we wouldn't expect it to, right? So that's false. Does F satisfy all the hypotheses between 1 and 2? Yes. It's continuous, it's differentiable, the derivative exists everywhere, right? And does it satisfy the conclusion of the mean value theorem? Well, yeah, it has to, right? I mean, it has to. If it satisfies the hypothesis, it has to satisfy the conclusion, right? It's a theorem, it's a proven thing, it's right. If you get an A, then you have to get the car, right? Otherwise, it's not a real promise, right? They broke their promise, it's not a true promise. The mean value theorem is a true promise, right? So if the hypothesis is true in for number 17, then in 18 it has to satisfy the conclusion. It says, and if so, find at least one suitable value to C. What? Have to be between 1 and 2, though. The only place you could get in trouble is if you said 1 or 2. It has to be between 1 or 2. So 1.1, 1.2, 1.3, 1.4, 1.5, right? At any point in between here, right, because the slope between the endpoints is just going to be 1. Any point in between here has a slope of 1. So that's right. So as long as you name a point between 1 and 2. Now, it so happens that the slope at 1 and at 2 is also, but that's not what it says. It says there is some point in the interior of the interval that has to have that slope. So you would have to name some point in between. How many are there? Infinite, right? There'd be an infinite number of points in between. Okay, so that's just a little bit more about what we were doing before with those other things. Okay, all right. I might make a comment if you look on page 286, if you just turn back or look back at the previous page there, the lemma, I don't know, lemma is another name for it. Lemma is like sometimes called a postulate, or a lemma is just it's not important enough to be a theorem maybe, even though they call it Rolle's theorem a lot of times. It's basically just an offshoot of the mean value theorem. It basically says that if the function is continuous on the closed interval and differentiable on the open interval, and f of a is equal to f of b. So if you've got a function that does this, whatever, it basically just says if f of a is equal to f of b, if the endpoints are equal, what's the slope between them? 0. So someplace in between there has to be a slope of 0, which of course is the most important slope for us, right? Stationary point where the derivative is 0, that's where max and mins occur, right? So of all the mean value theorem situations, maybe the most important one is when the two endpoints are equal. And then so if the two endpoints are equal, then there has to be a stationary point, you can say, in between them, so at least one. And that's what it talks about there. That's called Rolle's theorem. I'm not going to ask you about that, but anyway, kind of an offshoot of the mean value. All right, let's talk about the quiz. Well, I tell you what. No, let's don't do that yet. Let's talk about. Let's talk about, or have you do a few problems here, and then we'll let you ask some questions on exam 2. Okay, so I've got a few of these problems of the day to do here and show you. Okay, let's try this one right here. Now I'm going to give you, well, go ahead and read it. Now, one of the thoughts whenever you hear inverse is to interchange the x and the y. So you could write this as y equals x cubed plus x. Then you can interchange the x and y and try to solve for y. Unfortunately, you can't do that. You can't solve for y So that presents a problem. So I'm going to remind you of what I told you to approach on problems like this. You got the f function, you got the h function, and they are inverses of one another. So if you're going to try to find h prime of 2, that means you're going to have some point 2 something on the h function, right? Because 2 is going to be your input into your derivative, correct? That means on the f function, there's got to be a point that's what? Something 2. Now this would be a calculator problem, so you would get to use your calculator problem. So on the f function, it would match with something 2. So this point here would correspond with this point here. Okay? All right. Use that information to help you. Then the other thing I would tell you, or I would ask you, I guess, how are inverse functions, how are their slopes related? Remember? Here's natural log. Here's e to the x. They're inverses, right? This slope, if you were looking at mirror images, this point would probably correspond with that point. How are those related? Are they opposite? Aren't those both positive? So if this slope right here was, say, 3, do you remember what this slope would be here? Yeah, it was 1/3. They're reciprocals, but not opposite reciprocals, just reciprocal. Okay, those are some of my hints I'm going to give you. Okay, I'll give you a few minutes to see if you you will need your calculator to help you. But those are a couple of things I think you should always start with whenever you get one of these with an inverse. You got your two functions. If you know those two pieces of kind of information, it makes it not too bad.
still have to be numbers.
Yeah.
The highest is like, the highest, they have like 6 points. Rocket Ball against go. Which is consecutive every year.
All right, guys. Everybody just sit there. Easy. See, those two pieces of information, you just remember those. Because this is something we always struggle with. I'm confident you guys are the group to finally break this out. You guys are the group that's going to get this right. But it just, these inverse always just kill us. So what'd you do? Where'd you start?
So, for the two threat things.
Right there, right? That's the key. That's the part we never think of, right? Because this is the invert, this is the input, but it's the input on H, so it would be the output on F. So what'd you get? 1, get X equals 1. So that means that would be 1, which means H would have an output on 1, which we don't really care about. But then what? Then what'd you do? In the derivative. So then you do F prime, you get 3x squared plus 1. You plug a 1 into there, which would be 4. So this answer is 1/4. Okay? Because inverses have to have and I always just draw a quick little graph of e to the x and ln x and look at their mirror images. Remember, inverses would be mirror images, so there'd be a mirror right here, right? So it'd be that kind of a thing, and so I can always tell that they're both positive, so they're not opposite reciprocals, they're just reciprocals. All right, good. All right, let's do this one. Let's go to January. This one right here, number 12. Okay, give this one a try. Darn it. Don't tell me I'm not going to be able to do this. Dang it. Oh, I am recording. Darn it. I lost my... All right. I lost all my work, but that's okay. Have to do what?
Did you have to do this?
No. Because this is calculus class, and so in calculus class you better be doing what? When in doubt, you better be doing a derivative.
That's what I got.
Did you do a derivative?
Well, I did a derivative.
Okay, that's good.
But don't you have to know the speed? So you know how fast it's going?
Let's go back to what Jesse said. He plugged a 2 in to here, and he got 2 2/3. I agree with that. What's that tell you? So this is an object. We call it x of t because imagine it going back and forth on the x-axis, right? And so at the end of 2 seconds, it's at 2 2/3. That's all you know. So what else do you need to know how far it traveled? Where did it start? So how could you figure out where it started? So you plugged in a 2 and got 2 2/3. I agree. Okay, but you got to know where it started. How do you know where it started? Put a 0 in. What do you get? 2. So it started here, right? So how far did it travel? That's wrong. It did not travel 2/3. Because this is calculus, and in calculus you better do what? Better do a derivative. It started at 2 and it went to 2 2/3. What part of the story does that not tell? Huh? No, it's not going vertical. It's just moving. It's just horizontal position. It's just moving back and forth on the x-axis.
It went backwards.
What direction did it go? Right? We don't know. So why would we need the velocity? Which way did it go when it started at 2 and it ended here, but do we know it went straight there? No. So how do we tell if it went left or right? Number line. See if this is a basic problem. Now, we haven't done a ton of them like this. That's why I picked this one, right? So by next Wednesday, this needs to be a basic problem, right? We see something with position, right away we're thinking position, velocity, acceleration, especially these two. And the relationship is the derivative, velocity tells us which direction it's going. Left, right, that's our number line. That's like your maximum limit, right? So we need the derivative, which would be t squared plus 2t minus 3 equals 0, which would factor into t plus 3, t minus 1, which means t is either equal to negative 3 or 1. What information did that just find us? No, that didn't tell us which way it goes. What did that tell us? No, it didn't tell us velocity. Well, sort of. Come on now, what did that just do? X prime is a velocity. We said it equal, what does that mean, stationary points? Where we just found out where it stopped. We just found out when it stopped, right? When the velocity is 0 is when it was stopped, right? Because if it's going to turn around, what's it got to do? It's got to stop, right? So you got to do the derivative, set it equal to 0 to see when it stopped. And then, now the negative 3 we can ignore because we're only going between first 2 seconds, 0 to 2. So we need a number line, x prime number line. We put a 1 on it. We get a 0 here. We get a 2 here. Okay? There's a 1 there on our number line. So we put in a 0 right here. We get positive. 0 minus 1 is negative. Positive times negative is negative. And then we put in a 2. This is positive. That's positive. So this thing started out by going what direction? It went left. And then it came back to the right. So what do we need? What else do we need to figure out right now? How far left was it? How do we do that? When did it get its farthest left? We just figured it out. At 1. It got its farthest left at 1. It went left until 1, and then it turned around, right? So how do we find out where it was farthest left? Into the original, right? So we need, it's almost like a list of candidates, really, isn't it? Look what it ends up being. It's like the endpoints are plugged into the original, and it's where the derivative is 0. It's kind of like a list of candidates. It's very similar information, right? Now, we just don't want the max. We're not asking where was it farthest right or where was it farthest left. We're saying how far to go in between. So we're wanting all those things. So we put a 1 in here. We get 1/3 plus 1 is 1 1/3 minus 3. So that'd be negative 1 2/3 plus 2 would be what, 1/3? So what did it do? It went back to 1/3. So it went back here, right? So how far is that? From 2 down to 1 1/3, it went 2/3. And then it had to go back to here. From 1/3 to 2 2/3, how far is that? 2 1/3? So it went 2 1/3 on its way back. And then how far did we say that was? 2/3? From 2 down to, oh, no, 1/3 down here. My bad. So that's 1 2/3, right? So it went 1 2/3 down here to 1/3, and then it went 2 1/3 to get back to here, which adds up to what, 4? So it went a distance of 4. Okay, all right, we got to tuck that one away, right? We did that. We had a packet. We had a packet called the motion packet. You still have it, and we did a couple problems like that. One is at the bottom of the first page. There's another one farther in there where we talked about the total distance traveled, not net distance traveled. The net distance traveled would be 2/3, right? Where did it start, where did it end? That's net distance traveled. Total distance traveled, we got to find out where it turned around, and that's the derivative, set it equal to 0. Okay? All right, all right. So Let's go to number 13. Excuse me, man. Maybe I need a donut. All right, here we go. Find the equations of the two tangent lines to this curve that have a slope of 4. All right, where we start? Gotta do the derivative, right? Because that's what the derivative is, slope of the tangent line, right? That's what derivative is, the slope of the curve, which means slope of the tangent line. Yeah, you know, we don't have any home games this week. So. Immediately. Said first said went convenient. I said,
Just kind of realized that we get the same blocks.
it said what?
We need the same block.
Oh, you did?
Yeah.
So you think that one overrides your problem? Because that was probably written a while ago. Okay. All right. So, how do you know you got it? All right. So we got to do the derivative, right? We got to do the derivative. And then set that equal to 4 and solve it. And what do you get? Plus or minus 1, right? Plus or minus 1. So those are the 2 points. So now you just need to know 1 what and negative 1 what, right? And you get those by plugging into the original. So you plug 1 in there and you get 2. Plug a negative 1 in there and you get negative 2. And you already know the slope's 4. So bingo. There it is, right? Easy peasy. So you know the slope is 4. 1, 2. You know the slope is 4. Negative 1, negative 2. Equation of tangent line. There you go. Okay, good. So, because the equation of tangent line is all those things I've said, but sometimes we struggle with, but it seems like it should be pretty easy, right? So we know the slope is 4, so we do the derivative, set it equal to 4, get plus or minus 1, find the points, boom, right here. Just leave them like that, it's fine. Okay. All right, let's let you ask some questions. What do you got? Let's move over to exam 2. If you got a little bit of that done, if you ran into any questions there. Yes. Do you need that one yet? Okay. It's this one right here. And like these guys know, the first 2 packets, the sample packets, it says sample, that's in this book. The exam 2, that one, is in this one. Okay. All right, yes.
All right, 13 is there like a shortcut? So I got the answer to this.
I don't know, not really. You know, this kind of reminds me of that one that was in the other packet with that nth derivative one, kind of a pattern kind of thing. I suppose once you get going, but I'm not sure that it saves you that much time. I mean, so in other words, your first derivative, you know, you're going to kick out a 2, right? And then you're going to bring down your 3, and you're going to have 12, 2x minus 3 to the second. You're going to kick out another 2, right? And then you're going to have 24, 2x minus 3 to the first, and you're going to kick out another 2, right? And so when you do 4 derivatives, I've already done 3. So at this point, it's like, well, I might as well do another one, right? And then I'm going to bring that 1 down. I'm going to have 24. I'm going to have 2x minus 3. And then I'm going to kick out another 2, which is going to be 16, right? Now, did I do that right? Oh, wait, no, that'd be to the 0 power, actually, wouldn't it? Which would make that just be 1, right? So it's 24 times 2 to the 4th, so it ends up being that. So a shortcut, no. I mean, but the way they're written, that's why I didn't take the 4 times the 2 here and make 8. Because I noticed that I had this 24 here, and then I had like 2 to the 4th, 2 to the 3rd, 2 to the 5th, so I noticed that. So when I was kicking out my 2, and I knew I was going to kick out a 2 each time, I kind of figured that was the 2 to the 3rd, 2 to the 4th, so that I just kept leaving it like that, you know what I mean? Because remember, when you have a number out in front or over here, whatever, it just hangs out there. And then when you do this one, that wipes that out. So I guess the answer to your question is no.
Is that 2 to the 4th or is that
16
Yeah.
would be 2 to the 4th, yeah. 2 times 2 is 4, times 2 is 8, times 2 is 16.
I didn't know it was 24.
If what?
I thought I said 24.
Oh, no, this is 24. And then this is 2 to the 4th. Yeah, so that's right. Okay. All right, what else?
Do you have any
What's that? Yeah, you've got some of that other packet still.
like 7?
And sample 2.
Yeah, it's a limit one.
Now, is it one of those special limit ones that's supposed to look like a derivative?
It's one, I think it's one where you just have to give the H.
No, you don't? Okay. See, I thought we did one of these, but maybe it's the other class. Maybe the other class asked about this one and you guys did. Okay, so I'm glad you did. Because this is one of those where looks like a limit problem, but it's not really a limit. What does this look like? It's the definition of the derivative. Limit as h goes to 0, f of x plus h minus x all over h, right? That's 2 points getting really close together, and that's the derivative. That's the definition of the derivative. So we did a bunch of worksheets where we said, okay, what would be our f of x? Well, our f of x is where the x plus h gets plugged in, right? So this function must be absolute value x that we're talking about, okay? So if I had told you do the derivative of the absolute value function, right? When we were doing, remember the long way, right? That was this. Well, what would we do? We do f of x. Remember f of German shorthair? What do? You put a German shorthair in for x, right? So f of x plus h, we put an x plus h in for x. So we put an x plus h right there, we get that. Put an x in, we get that, all over h, right? This is what we would get. So what this question is really asking is what is the derivative of this? Because that's what this is, the definition of the derivative. What is the derivative of this the derivative of this at 3? Well, here's the absolute value. What's the derivative at 3? It's a slope, right? What's the slope at 3? It's 1. Now, let's quickly review this, okay? Because I know I've got some in this thing right here. Let me find them right here. Tricky limits that are actually derivatives, okay? Handy. Okay, so find this limit, right? Find this limit. Well, we're not really finding that limit. What we're recognizing is this is actually asking us for the derivative of what function? This is the sine function, because what do? We take the pi halves plus h, that's a German shorthand. We plug it in where the x was. So this is the sine function, and they're wanting the derivative at what value? Pi halves. So this problem is really asking for the derivative of this at pi halves. So what's the derivative of sine? Cosine, and at pi halves. Well, what's cosine of pi halves? 0. So the answer to this is 0.
Can we do just like a regular limit problem?
We could find one, but I would make sure we do these because these are probably going to be on there too, right? Okay, let's do another one. Okay, what's this function? This must be what function they're asking us to do the derivative of. Because whenever you see that 4 plus 8, this must be the square root of, no, it's not square root of 4. This was plugged in where the x was. So square root of, just square root of x, right? So the function square root of x at 4, right? Because this here would be square root of 4 right here, right? Okay, because it's f of x plus h minus f of x all over h. So if I told you to do this derivative at x equals 4, what would you do? You would plug x plus h in for there. So you get square root of x plus h minus, and then f of x would just be square root of x all over h. Now if I wanted you, not x plus 4, it's x plus h. Now if I told you to do it when x is 4, you would get square root of 4 plus h minus square root of 4 all over h. See how that's what that is? Right? So this is square root of x. So this is asking us to do the square root of x, so that's x to the 1/2. So the derivative of that is 1/2 x to the negative 1/2, and it wants us to do it at 4. So that's 1/2, 1 over square root of x, right? So there's our derivative. Plug in your 4, so that'd be 1/2 times 1/2. The answer to this limit problem would be 1/4. Okay? It is not asking us to do a limit problem, it's asking us to do a derivative. Right? It's a derivative. We got to recognize what that derivative is. Okay? Here's another one. What is this function? This is not really a limit problem, it's a derivative problem. What's the function? X to the 5th. This right here is where the x was. Okay, x to the 5th. What's the derivative? 5x to the 4th. Then we want the derivative at 1. So it's 5. So the answer to this
How
problem
did
is
you know that it was, I'm confused, that makes x.
because when we did these problems the long way, before we knew our rules, I said, okay, let's do the derivative of x to the 5th. And the formula was limit as h approaches 0 of f of a plus h minus f of a all over h. That was our rule. That was our rule. So if I want to do this derivative, if I told you, okay, let's do this derivative at a equals 1. That's what we want to do. So what we would do is we'd say, okay, let's put in a 1. So we want to do f of a plus 1 plus h minus f of 1 all over h. So we would start there, right? And then we'd say, okay, this is our f of x. We'd say, what's f of 1 plus h? Well, this is German shorthand, right? We take our 1 plus h, we plug it in where the x was. So that would be 1 plus h to the 5th minus, now f of 1 would be 1 to the 5th all over h. And then we would FOIL that out and we would do all that stuff, right? But now what I'm telling you is let's work this backwards. So now we're trying to say, okay, let's start with this and let's see where it came from, right? This 1 plus h, where did that come from? It came from right here. What did we do? We took that and we plugged it in where the x was. So when we see this 1 plus h in this problem, we know that's where the x was. So that's why we know that function is x to the 5th. Okay? All right. So, but remember, 65% is an A. 65% is an A. You can miss this one. You can still get an A, right? Now, it'd be nice not to miss it because it's not very hard, right? Once you get the hang of what's going on. Okay? All right. Now, you said, is there an actual limit one? Is there one you're thinking of in your packet or something?
I just forgot how to do them. Like,
There's one on 9, exam 2. Our new packet. There you go. There's one. Did you do that one yet, Emily? This one's an infinity, right? So what do we think of when x goes to infinity? When x gets really big, what's happening up here? It's getting bigger and bigger and bigger, right? I mean, squared, right? Million squared, billion squared, right? What about the minus 6? Now, we could say, well, it's getting really big, and what about this? It's getting really big, but negative, right? So it's like infinity over infinity, so we could do L'Hopital's rule. Or we could just say, what happens to this minus 6? Doesn't matter, right? So this really, high powers dominate. So when x gets really big, really only the x squared matters. What about down here? Really, oh, oops, I need that negative. But those don't matter either, right, when x gets really big. So this becomes negative 3x squared, right? And the high powers dominate when x is going to infinity. So what happens? The x squareds cancel? Negative 1/3. So that'd be one example. And then the one I was just gonna do there a minute ago. Right? What if you had something like that? So what's the first thing you do in a limit problem? You substitute a 2 in, right? But then those other ones we didn't. And the reason is when you see limit is h approaches 0, right away that's your trigger. Boom, 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 boom. This is not a limit. This is not a real limit problem. This is derivative. This is the definition of the derivative, right? That's a, like it said, tricky limits that aren't really limits. They're actually derivatives, right? But regular limit problems are like this. X approaches 2 or x approaches infinity, something like that. So what do? You plug in a 2, you get 0 over 0. 0 over 0 means what? Keep going, right? Now we can do L'Hopital's rule. Or we could, this one, it's easy, right? We just factor. So x plus 2, x minus 2. So the keep going can be some algebra maybe. And then what? Now we can plug in our 2. 2 plus 2 is 4. Right? Does that ring a bell? I mean, those were what we did on basic limit problems. So some algebra or high powers dominant, that kind of thing for
So
infinity.
then you get a number over 0, that was my reason. That's all it says.
If you get 6 over 0, that doesn't exist, which means basically vertical asymptote. So we would look on the left, look on the right, and maybe it's going to positive or negative infinity, that kind of thing. Right. Okay, what else? Anything else? Excuse me, man. On sample 2? The function has a, yeah, I like these ones with the B. We're going to do some more of those like on Monday, especially. But with the A in there and the B in there and so forth. This function has a horizontal tangent and a point of inflection for the same value of x. So horizontal tangent means what? Slope is 0, derivative is 0. So let's do the derivative. So y prime would be 4x cubed plus 2bx plus 8, and that's got to equal 0. Right? So that's horizontal tangent, slope has to equal 0. Now what about a point of inflection? Now it actually can't be a max, it's going to have to be a flat spot, isn't it? If it's a horizontal tangent and a point of inflection, both, it's going to have to be that, right? It's going to be a flat spot, but whatever, it doesn't matter, that part doesn't matter. But what do we do for point of inflection? The second derivative set equals 0. So we do the second derivative, we get 12x squared plus 2b equals 0, right? Now, this is like two equations, two unknowns. That's why I was telling you the other day, anytime you get these A and B's or K's or something there, a lot of times it's two equations, two unknowns. Do a substitution, or, and now in this case it could be a substitution, or you could just set them equal to each other. Now the problem with setting them equal to each other is it kind of gets kind of messy, right? Like I could set this equal to this, and then I could do that, but it starts to get kind of, I think substitution's a better bet. So what I would do, to be honest, is I notice this 2b right here. Now this, I'm going to be a little tricky here, but I'm going to solve this one. I'm going to move this, I'm going to solve for this right here. See this 2b right here? And I got a 2b right here. So don't those two have to be the same? Right? So I'm going to do 2b. Now you might say, well, just divide by 2 now and solve for b, but then I'm going to multiply by 2 again anyway right up here. So in place of that 2b, I'm going to stick that right there. So I'm going to get 4x cubed plus, and now I'm going to put negative 12x squared in place of that 2b, and then I got another x there, plus 8, and that equals 0. So look what happens, something really nice. So I get 4x cubed, this will be negative 12x cubed, plus 8 equals 0. So I get negative 8x cubed, plus 8 equals 0, and this is going to work out nice, because now I get 8 equals 8x cubed, x cubed equals 1, x equals 1. So, but then, now, here's the tricky part. And I did all that work, and I get x equals 1, and then I go to circle C, and I realize that is not the right answer. Because that's the value of x. They want the value of b.
How did you get 12x cubed when it's 12x squared?
Times x. Because I substituted for that 2b right there.
So which one do you have to point in the
No. You should, right here. Plug in right here. I just need b. So x is a 1, so I'll just put a 1 right there. Right. I mean, I could plug into whatever, but why? I could. You're right. I could plug a 1 into here. Right? I can plug a 1 into here for x. I can plug a 1 into here for x, which is basically what I'm doing. whatever, wherever you can get a b. If I put a 1 in there, I get negative 12, divided by 2, I get negative 6. So the actual answer for b is negative 6. Right, because I'm putting a 1 in for x right there. But I could put it up here. If I put a 1 in for x right there, I get 4 plus 2b plus 8 equals 0. Subtract that 4 and the 8 over negative 12, and I get b equals negative 7. You've got that connection there between x and b, so you can take advantage of that. Okay? What else? Speak up, speak up if you want. 13 on sample 2.
You're just finding y prime, aren't you?
No, we just did that. Oh no, that's a difference.
Is that-
Yeah, you're just finding y prime, just implicit differentiation. Don't forget to do the product rule right here. Okay? Now, I think it comes out to be c. Now, when I did it, I think the other class, we worked this one, but when I did it, I got y minus 1 and 1 minus x like that. Well, if you take a negative out of the top and a negative out of the bottom, then that turns into that. If you take a negative out of here, you get that, and then the negatives cancel. And so, you know. So it just depends which side you get your y primes on. So you have to be able to understand that.
Wait, if you're doing a y prime, then you only do like.
There's no x primes. Right, there's no x primes, because look what you're doing here. You're doing the derivative with respect to x. So x prime would just be dx over dx, which is 1. So yeah, you only tack on a y prime on the ones where you have do the derivative. Okay? Any more? Any more? I know you haven't had a chance to work a lot in this packet, so.
Number 1 on like sample, or not sample, example 1 or 2.
Our newest one?
Yeah.
Which one?
Starts on the calculator problem. Multiple choice calculator problem.
Oh yeah, now these are numbered differently. Notice, so this this goes up to 28, and then it starts over at 1, where the other one it went 29, 30, you know. So yeah, so which one now?
That one, wouldn't this one just be 1, 2, 3?
Oh, the very first one?
Yeah, what is it saying that like functions have a derivative?
Well, if it doesn't have a derivative, it means it's undefined.
Yeah.
So it's like a sharp point. Now this is a calculator, so you could graph them, right? You could graph them. I think what happens is, well, because they're tricky, because we can't really do a derivative rule on these because we don't really have a derivative of this. So I think one of the things you could do is graph them. Now this one you actually could do the derivative of. Derivative of the top e to the x, leave the cosine alone, minus the top left alone, derivative of the bottom is negative sine, which would be this. It's good to practice our quotient rule once in a while. Cosine x, quantity squared. So if you put a 0 into here, e to the 0 is 1, cosine of 0 is 1. So that's 1. Sine 0 is just 0, so that's that. And cosine of 0 is 1. 1 squared is 1. So I know that has a derivative at 0, right? Because I just did it. I did the derivative, plugged in at 0. Okay? But these is harder to do, right? And so the absolute value. So I'm not sure on this one. So it's like, where is the vertex of this is kind of the key. Where?
Well, that one could be undefined too.
What's that? Yeah, so I think graphing them would be the key. I think graphing them would be the key, because you plug 0 into these and you get 0, right? You plug 0 into this, you get a really small number. But you can look at it and see if there's kind of a sharp point there, and you can tell pretty quickly. What is the right answer? Do you know? It's all of them. It is all of them. I think it's E. It's 1, 2, and 3. And they show in the answer book here. They show some pictures. Because I think what happens on X cubed, it's one where it comes down nice and smooth, and then it kind of goes like this. Well, when you put the bars around it, what's that do? It just flips this up, right? And so this part just flips up here, but it's nice and smooth. But sometimes, you know, if you get a graph, you know, if it crossed the x-axis, say here, and you flip this up, well, what's gonna happen? You're gonna get a sharp point there, right? So, so that's where you would run into some trouble on a cube. So you pretty much just have to, look at that and tell, and again, they show some pictures here, and they give, it shows it the nicest. Okay? All right. Well, I'll let you guys just work then on this. Towards the end of the period, I'll give you the take home. Now tomorrow we'll do the quiz. When you get done with the quiz, you can work on your take home. You can keep working in the packet. Probably won't have the last packet ready for you till Monday, unless somebody really, really wants it, because that would still give us all day Monday, most of the day Monday, most of the day Tuesday to work on that last packet. And the last two packets, remember, aren't due till Thursday, so you have Wednesday night to work in that packet. So, you know, you get all the packets done by the weekend, and then you don't really have much to work on, you know, as you lead up to the midterm. So I think you just want to kind of keep working steadily. So, okay, so go ahead and keep working in those and for the rest of the time. If you got any other questions, like, you know, Scott, especially, like, get back in the samples, if you didn't see in the videos or something you want to ask me about, look at the answer books, whatever, be glad to help. Should be 1. I don't see your 1, but you should try it. So 1 plus y prime equals, and then this would be derivative of x is 1 with the y left alone, plus, so remember you got to do product. Product. Derivative of x is 1, y left alone, plus x left alone, and derivative of y. And then you'd have, right, and then you'd have your minus 1 if you want to minus u. Because over here it was a 1 plus y prime. Now you got to get the y primes on one side. So yeah, go ahead. So are you going to maybe not come back here? Take this then. That's the take home. It just work them out on separate papers.
Is it?
That's just